All right, so today we are talking about section 9.0. It's not really a section in your textbook. It sort of goes along with section 4.8 in your textbook. If you really want a reference, you could look at section 4.8 in your book. So we are talking about congruence transformations. Create congruent figures using transformations. For our warm-up, we were asked to find the length of AB if A is at 2, 7, and B is at 7, -5. Who remembers how to find the length of a segment given coordinates? There was a formula we learned for this. The distance formula, does anybody remember what it is? Ari? There's a long square root thingy. We usually start with the x's, like x2 minus x1. Okay, what do we do after we subtract those x's? Square it, and then plus y2 minus y1, whole thing squared. Okay, it's coming back. All right. When we plug things in for the distance of AB, what do you want to put in for your first x? Okay, 7 minus the other x. 2, that gets squared. Plus, what do you want to plug in for y? Or what do you have to plug in for your other y? -5 minus 7, that gets squared. All right, if we take 7 minus 2, what do we get? And then we square it. 25 plus -5 minus 7. It's -12. Square that. A positive 144. Add them together, we get 169. The square root of that is 13. That is our distance. Questions about that process? Okay. What unit is 6 units to the right of 3, 5? That would be up. 311 would be up. 9, 5. Good. 9, 5 is going to be 6 units to the right of 3, 5. So remember, your x coordinate moves you left and right. Your y coordinate moves you up and down. Questions about number 2, Ataya?
So if it's at like 3 units up, you would change the y coordinate?
Yep, up and down we change the y coordinate. Left and right we change the x coordinate. Anything else on that one? Okay. Number 3 asks, do you think these 2 triangles are congruent? Why or why not? Paris, what do you think? Why? I don't think we have to use a specific term. I agree that these are congruent, but we have to say why we would think that they are congruent. Kobe, what do you think? You're getting there. Akira? We could argue it that way. I think Kobe was a little closer. Kobe, you want to reword it? No, that has to do with perpendicular. We don't really need that. Ataya, what do you think? That would be part of it. I think we're still making it too hard, though. Kara, what do you think? Good. So all the side lengths are or corresponding side lengths are the same or equal. That's the definition of being a congruent figure, is that you're not changing your side lengths. Okay, so, well, we'll get a more formal definition in a minute. But if all these segments are congruent, if all the segments from one figure to the next are congruent, then the figures themselves are congruent. So we could say yes, and we could say something like the distance between the points is equal or the same. Corresponding side lengths are congruent. You could use things like slope to kind of argue your point. That would get into the fact that these side lengths would have to be congruent if you're using the same rises and runs. Questions about our warm-ups? Ready to move on? Okay. On we go. Our formal definition for congruent figures. Figures, one of which is the image of the other under a reflection or a composite of reflections denoted by congruence. So that is kind of wordy. So, a transformation is what we're going to talk about today. A transformation is an operation that moves or changes a geometric figure in some way to produce a new figure. So in the warm-ups, that last warm-up we saw that had that picture to go along with it, that showed a type of transformation. They moved the triangle to produce a new figure. The new figure is called the image. So the new figure, the final figure, is called the image. A transformation can be shown using an arrow. So a very, very basic example of that would be to have some sort of triangle. And then we use an arrow. Sometimes it'll be like skinny. Sometimes it might be more of like a bubbled in or thicker arrow. And we might show that like we moved it down slightly. So they ideally, or in your textbook, they will be like the same exact size. They'll just be moved a little bit. They could be flipped over, turned around, flipped upside down. We'll see all those sorts of examples. If you look below into those boxes, you'll already see some of them shown there. Questions in general about congruent figures or transformations? Okay, on we go then. The three main transformations are translations, reflections, and rotations. So a translation moves every vertex of a figure the same distance in the same direction. Okay, so a translation will move it the same distance in the same direction. And when they talk about a vertex, they're talking about those corner points. So this figure has several vertices. So all those vertices or all those corner points are getting moved the same exact distance in the same exact direction. A reflection uses a line of reflection to create a mirror image on the original figure or of the original figure, might be a better way of saying that. Okay, so they showed the line of reflection here. So if we were to make this into a piece of paper, print it off, or like you could do it with your notes, and we were to fold it along this line that they showed, then these two images should match up with each other exactly. Should sandwich right on top of each other. Questions about reflections? Okay. Finally, we have a rotation which turns a figure about a fixed point. That is called the center of rotation. Questions, concerns, need more time on this slide? Okay, we'll move on. Name the type of transformation demonstrated in each picture. So we're picking from that list from the last slide. Letter A, we are saying is a what? Good, reflection. If we were to fold this in half along that axis, then those would sandwich on top of each other. What about letter B? B is a rotation. I think it can be a little tricky to see, but it's clear that we turned it upside down somehow. So this is a rotation. And the last one is a translation. All we did was slide it over. Questions, concerns? Hearing a bunch of flipping, so I'll take it we are ready to continue. Let's look again at example 1C and name the coordinates. See what we notice. So we'll start with the green figure, well, at least it's green on the board, the solid one. And I'm going to name these points A, B, and C. So let's name the coordinates for A. Anybody find them? Good, negative 4, 2. Remember, if we go left of the origin, we're negative on the x-axis. All right, what about letter B? Point B? Negative 1, 3. And point C? Negative 2, 0. Now, when we do some sort of transformation, this is a notation thing, usually your new points will be labeled with primes, and they look like little apostrophes. So A would move to a point that we would call A prime. It's got a little, kind of looks like an exponent of a 1. Some people think it looks like an apostrophe, but we call it a prime. B would move to B prime, and C would move to C prime. And then we could find the coordinates of those points. A prime, B prime, C prime. Sometimes you'll see them labeled as completely different points. Like if the original is ABC, then the image might be DEF. Sometimes they'll use completely different letters, but sometimes so that you can see which point moved where, they'll label it with primes. Questions about the prime notation? Okay, then what are the coordinates of A prime? 1, 0. What about B prime? 4, 1. Okay, and C prime? 3, negative 2. So the question is, what do you notice? Is there anything that you notice about the coordinates from the original to the image? In my opinion, it's easiest to see a relationship between the y coordinates and the new y coordinates? You want to focus on that first? What happened to my y coordinate every time? We subtracted 2 from it every time. See, the a minus 2 gives us 0, 3 minus 2 gives us 1, 0 minus 2 gives us negative 2. What happened to the y coordinate every time, or the x coordinate every time? We seem a little divided. I'm going to agree with the add 5. Negative 4 plus 5 is 1. Negative 1 plus 5 is 4. Negative 2 plus 5 is 3. Okay, so remember that translations move every vertex the same distance in the same direction. Questions about this slide before we move on? Okay. So, now we see it officially. You can describe a translation by notation x comma y with the arrow. So x comma y goes to x plus a comma y plus b. So that shows that each point x comma y of the first figure is translated right a units and up b units. Assuming that we're using addition, if we were to use subtraction instead of going right, which way would it go? Left. And if we subtracted b, it would go down. Okay, so if we were adding, we're moving to the right or up. If we're subtracting, we're moving to the left and down. And it's possible to mix and match. So we could be moving to the right and then also moving down. That's what the last example that we just looked at did. Questions, concerns about the notation here? Okay, so like on that last one, it would have been shown x comma y, arrow, x plus 5 comma y minus 2. So we were adding 5 to the x coordinate, subtracting 2 from the y coordinate. So if you want to write that by that last example above, so that you have an idea of what it's going to look like. Are we ready? Okay, on we go. All right, figure ABCD has the vertices. They list them out. Sketch ABCD and its image after the translation. And then they use that notation. X comma y goes to x minus 1 comma y plus 3. So I'm going to give you a couple minutes to work on that. So you're going to sketch the original one and its image. To sketch the image, it would be helpful to fill in the coordinates of the image. Notice that they use the prime notation here. So A would go to A prime. I'll give you a couple minutes to work through that. There are a lot of directions there, and then we'll talk about it. All right, who wants to tell me what they got for their coordinates for A prime? Kobe? Negative 2 comma 5. What about B prime, Paris? 1, 6. Maj C prime? 4, 3. And D prime, Ari? 0, 2. Do we all agree with these? Okay, we should have taken our x coordinates and subtracted 1 every time. So negative 2, 1, 4, and 0. Good. We should have taken our y coordinates and added 3 every time. So 5, 6, 3, and 2. I agree with all of those. Then the last thing that they wanted was for us to also sketch the image after the translation. So I am going to switch colors to do this and maybe use a dotted line instead of a solid line. So if we sketch -2, 5, how do I get there from the origin? Left how many? And then up 5. So that's my new A prime. I could, if I wanted to, have just taken my A point and said, well, -1 means I'm going left 1 from there, and y plus 3 means I'm going up 3. So we could use our points to help us out. So if I were to start at B, instead of graphing those coordinates, which would not be that challenging, I could start at point B and say I need to go left 1 and then up 3 to get my B prime point. B prime, same thing with C, left 1, up 3 to get my C prime. Left 1, up 3 to get D prime. And we can see that they are, of course, overlapping. That's fine. If you wanted to do a different color or a different type of line, like a dashed line instead, that would be fine. But these figures should look congruent. Questions, concerns? We feel good about translations? Okay. We'll move on. Let's jump back to example 1A and name the coordinates and see if we notice anything. So on 1A, again, I'm going to call these A, B, C, and D. And then on the other one, the image, I'll call them with their primes. I'll give you a minute to get those filled in before we go through them real quick together. All right, where is point A? 4, 5? What about point B? 3, 2. C? 4, -1. And D? 1, 2. What about A prime? -4, 5. B prime? -3, 2. C prime? -4, -1. And D prime?
-1, 2.
What do you notice?
The x's are the opposite of the.
Okay, the x's are opposites and the y's
Same.
are the same. And they reflected it over the y-axis. So anytime you reflect over the y-axis, the x's are opposites, the y's stay the same. Now we've got other rules that we'll talk about for reflections in general, but it's important to notice these things. Are we ready to move on? Okay. So here are the rules stated out a little bit neater. So let's start with reflection in the y-axis because that's what we just did on that example. So which coordinate got multiplied by -1? The x coordinate. So for a reflection in the y-axis, we multiply the x coordinate by -1. So it becomes -x, comma y. The y stayed the same. If we are instead reflecting in the x-axis, what do you think gets multiplied by -1?
1.
The y-coordinate, and which one would stay the same? The x. Multiply the y-coordinate by -1, and the x stays the same. So if we use that function notation, the x is the same, and we have the opposite of y, or a -y. Questions about these rules?
No.
Okay, ready to move on? No. Okay. Now are we ready? All right. You are drawing a pattern for a cross-stitch design. Does anybody know what cross-stitch is? Okay. So for those of you that don't know, cross-stitch is when you have thread and you usually have like, it's generally on some sort of circular thing that's holding a fabric taut, and you use a needle and thread and make little X's to form some sort of picture. Does this sound familiar to anybody? Okay. So it's really nothing. This would be a Christmas tree cross stitch pattern. Okay, so if this were a cross stitch pattern, you would be putting all your little X's with your thread along these lines as you do your project. Okay. Typically cross stitch is associated with, like, grandmas, but anyone can do it. All right. Use a reflection in the y-axis to draw the other half of the pattern. So, what might help would be to mark your points. Not that one. Notice that I'm using like any corner as a point. Now, if we are reflecting in the y-axis and we have a point on the y-axis, is it going to move? No. So any of these points that are on the y-axis are going to, stay exactly the same. So if we go through this point, the next point down is going to be at -1, 2. So when I reflect it, what's its new point? So
1, 2.
Good. We change the sign on the x. We keep the y the same. So it would become +1, 2. If this point here, my next one down, is at -2, 0, its reflection would be where? 2, 0. Change the x, keep the y. Now, of course, I'm not even talking about ones that are on the axis because those are going to stay. If you want to be filling in the rest of your Christmas tree as you go, you could be connecting these points together. All right, so we keep on going down. I've got a point out here at -3, -3. Where is it going to go? 3, -3. Good. All right, bless you. Next, we've got a point kind of inside here, the top of the stump of it. -1, -3 moves where? 1, -3, and then, of course, that point down at the bottom is on the axis, stays on the axis. We've got one last point at -1, -4. It would move to 1, -4. I can finish connecting the parts of my tree. Questions, concerns? When you do this, if you're sketching it especially, you should end up with a mirror image, meaning if we fold it along the axis, the y-axis in this case. They should sandwich on top of each other. Questions, concerns? Ready to move on? Okay. Once again, we're going to keep with the same pattern. Let's look at example 1b. Name the coordinates. What do you notice? So again, I am going to label this as triangle A, B, C. We'll list out its points. And that means when we rotate it, we will have points A prime, B prime, and C prime. All right, what do we get as our coordinates for point A? 2, 4. B? 2, 1. C? 4, 1. All right, what about A prime? -2, -4. B? Okay, and C? Questions about these? What do we notice about them? Both X and Y change signs. So we have the opposite of each of these. Now we have different types of rotation, so we have different rules for those different types, much like we did with the reflections. But this is one type of rotation where we just negate both coordinates to get our rotation. Questions before we keep going? Okay. On we go. In this lesson, if a rotation is shown in a coordinate plane, the center of rotation is the origin. That's important. That makes our lives easier. The direction of rotation can either be clockwise or counterclockwise. Do we all know what clockwise and counterclockwise mean? Yes. Okay, good. Now, sometimes you might see clockwise abbreviated as CW and counterclockwise abbreviated as CCW. Clockwise, counterclockwise. The angle of rotation is formed by rays drawn from the center of rotation through corresponding points on the original figure and its image. So just to show you in these diagrams what that means, we're being told that this is a 90-degree clockwise rotation. Give you a second to flip your page. We all see that box, 90 degrees clockwise rotation? Okay, so that means that this would have had to have been our original image, and then we're getting our new image over here. So our origin is the center of our rotation. So let's say I'm going to go through these 90-degree right angle corners from my original to this one. So if I form rays that go through those points, I can see pretty easily here that I've made a 90-degree angle here. That's why this is considered a 90 degrees rotation. Does that make sense? Yeah. You can do the same kind of thing on the other one. Again, our origin is our center of rotation. I usually think it's easiest to use your right angles if you have them to make sure we're using the correct corresponding figures. I understand that in this case it kind of runs down into that logo at the bottom here, but we can see this angle would be a 60-degree angle, a clockwise rotation. We can technically rotate at any degree, clockwise or counterclockwise. Okay, so it just depends on what the problem asks us to do. There are certain rules we'll get into later about specific rotations, like 90 degrees, 180 degrees, and 270 degrees. Now, if we were to rotate something 360 degrees, what do you think happens? Good, you go back right to where you started. So usually we won't do that because it's not very interesting. Questions about rotations before we move to the next slide? I know today's notes are rather long. It's a big introduction to our transformations. Note that rotations preserve distance from the center of rotation. So, segments drawn from the center of rotation to corresponding points on the figures are congruent. Questions, concerns, need more time on this slide? Just a bunch of warm, fuzzy feelings. Okay, we'll keep it going. Graph segments A, B, and CD. Tell whether CD is a rotation of AB about the origin. If so, give the angle and direction of rotation. Okay, so lots to do here. First, let's graph AB and CD. So AB is at -3, 1, and -1, 3. Connected, that's my AB. I'm going to switch colors for CD just to make it a little more clear. C is at 1, 3. And D is at 3, 1. So we have to decide if this is a rotation from AB to CD. If so, give the angle and direction. Now, direction should be pretty easy to know right away. If this is a rotation, which way did it go? Clockwise, right? We started here, we move around our clock, so we would go clockwise here, and then we have to decide if we think that this has an angle about it. So I would look from the origin, and I would go through from the origin, draw a segment that goes through A. And if I'm going through A, which other one should I go through? C.
I thought it would be D.
I think that we would have to go from A to C. If we started this segment with A, we got to start this one with C. Does that make sense? Okay. So if we're talking about segments A, B, and C, D, right? A came first, C came first. So what kind of rotation would it be? 90-degree rotation clockwise. All right, on letter B, let's graph them real quick. So A is at 0, 1, B is at 1, 3, C is at -1, 1, D is at -3, 2. What?
It's 0. It's negative 1.
Oh, you are correct. Switched them around. Negative 1, 1. Negative 3, 2. That looks better. All right. So we have to decide if we think this is a rotation about the origin. I see some people shaking their heads no.
No.
Anybody think it is? So there's one easy way to know that this would not be a rotation. Rotation preserves distance. Are these the same length?
No.
No. We could easily see if we were to draw these into right triangles that these are not going to have the same. Oh, actually, they are. They would have the same length, but the issue is going to come in with rotating about the origin. If you rotate about the origin, is this point going to move?
No.
Like by 1.
I don't know.
I think that this one's going to be a little trickier to say in the next 2 minutes. So let's revisit this one tomorrow. Part of it's going to have to do with if we form the same angle both times. So let's come back to B tomorrow.